Hey guys, Andy Robertson here with CQE Academy, and I'm back with another video to help you prepare for the CQE exam, where we're talking about reliability. Now, in terms of the CQE exam, reliability is one of the most important topics on the exam, and I think it has more questions than any other topic in the body of knowledge. So this is a really important lecture. Now, we're not going to cover the entire reliability section today. We're going to talk about two things: reliability indices and reliability models. All right, so let's head over to the computer and get started.
All right, let's take a quick look at today's agenda. I want to start over here on the left with the CQE body of knowledge. So no matter what exam you're studying for, reliability engineering or quality engineering, whatever, they have similar bodies of knowledge. But here in the CQE body of knowledge, we want to talk about reliability and maintainability indices, mean time to failure, mean time between failure, and we'll start the presentation off with that. So we're going to start with failure rate, mean time to failure, those sorts of things. And then we're going to get into reliability models, things like the Bathtub Curve, the Exponential Distribution, and the Weibull Distribution. By the way, we'll save things like here the maintenance tools, and you'll also see like hazard tools like FMEA. We'll cover that in a different video, but today we're just going to focus on these indices and the reliability models. Okay, so I want to start with just a basic definition of reliability, right? You're watching this video, so you have some understanding of it, but essentially the formal definition is that reliability is the probability that a product will perform successfully under specific conditions for a given period of time. The key phrase here is a given period of time. You know, reliability, the way I like to explain this is that reliability is quality over time, right? We build these products, we make these products, we use these products, and we expect that they're able to perform at a certain level over a given period of time. And so that's how I want you to think about reliability, because there's very much a relationship between reliability and time, right? We expect high quality over time. All right, so let's get into those reliability indices. The first one I want to talk about is called the failure rate. This is the most basic reliability index, and it simply describes the rate at which your product fails over time. And I've included a bunch of pictures here, right? Light bulbs fail, lawnmowers can be used for a particular period of time and then they fail. And that's essentially the failure rate. And so oftentimes we like to talk about the rate at which a product fails over time. Now, the more meaningful metric that you'll hear most often is something like mean time to failure. Now, I want to explain this to you because this is a reliability index for non-repairable units. Now, I want to make a huge distinction here because there are products that we make, and this light bulb is the perfect example. We make it, we start using it, we expect it to work properly for, let's say, 10,000 hours, and then when it breaks, we have no plans on repairing it. We're just going to throw it out. We're not going to fix it. We use the light bulb, and then we're going to throw it out. There are a ton of items out there that we produce and that we use that are considered non-repairable units, right? This AC motor, this light bulb. And when we're using a non-repairable unit, we always talk about this reliability indice called the mean time to failure, right? It's what is that average length of time until that product fails. Now, the inverse of that is called the mean time between failures. So when we're talking about the reliability of a repairable unit, we want to talk about a metric where we start using it, and then we use it for a period of time, and then it breaks, and then we fix it, and we start using it again, right? So things like common appliances, automobiles, lawnmowers, airplanes, these items all are repairable. And so when we're talking about a repairable item, in your head, if you produce a repairable item, the metric that you're going to use is mean time between failure. In fact, and I'll show you this on a future slide, but these two indices are identical to each other in every single way, except for this one distinction between non-repairable and repairable units. So in your mind, I want you to think of these two indices as very much identical. And again, that only difference is repairable and non-repairable units. And before I give you an example, I want you to know we're going to work an example from both these indices so you can see how they're calculated. I want to start by showing you the equations that we use for all three of these so that you understand the relationship. So when we're talking about the failure rate up here, we calculate that as the number of failures divided by a certain period of time, right? And you'll kind of see that this is generally reported as failures per hour, okay? This is the rate at which your product fails over time per hour. Now, this isn't a very meaningful metric because our customers never really talk about our products in terms of the failure rate. If I'm the customer and I'm describing my refrigerator or my automobile or some other repairable unit. I'm going to describe that in the form of time, right? I want to buy my fridge and I want it to work for 6 years, 7 years, 10 years. I'm going to give you a unit of time that I expect the product should be able to last before it breaks. And that is the mean time to failure, or the mean time between failure. Now, the reason I wanted to show you these equations here is because I want you to see the variables, right? Essentially, this equation is simply just inverted. When we're calculating the mean time to failure or the mean time between failure, we're simply just taking the inverse of the failure rate, and it reflects the amount of time that passes before we have a failure on average. Now, you'll also notice that we use the same Greek letter here, theta, to represent mean time to failure and mean time between failure, and that is absolutely on purpose. Remember, these two indices, these two indexes, are identical in every single way, except that mean time to failure is non-repairable units, and mean time between failure is talking about a unit that is repairable. And then I just want to kind of summarize this slide by showing this relationship. The failure rate, which is lambda, is the inverse of theta. It's the inverse of mean time to failure, and vice versa, right? Our mean time between failure, or our mean time to failure, is simply just the inverse of the failure rate. So that's the relationship between these two indexes. By the way, before we move on, I know I've thrown a lot of equations at you. This presentation will have a lot of equations, and I want to give you a cheat sheet that you can use on the CQE exam. Just head over to cqeacademy.com/free cheat sheet. It's got all these reliability equations, and I'll give you a practice exam for reliability specifically to help you use these equations, help you practice and prepare for the CQE exam. All right, let's keep going. All right, now let's do an example of a failure rate. So let's say we have 20 units, and we put them on test. We start running them at their normal operating condition, and we run all 20 units for 1,000 hours. In that time period, 6 of those units fail at the following hours, right? You can see those hours here. What is the failure rate of the product? Now we can use our equation here. So let's see what we've got. The failure rate lambda is equal to the number of failures. Now remember, we had 6 out of the 20 units fail, so we had 6 failures. And then in the denominator here, we have the operating time. So for those 6 units that failed, we can simply just take those data points right out of the problem statement and put them in here. Now, the other thing you have to consider, and this is the biggest mistake people make when they calculate the failure rate, is they don't account for the time associated with the products that didn't fail. So we had 14 units that made it the full 1,000 hours of testing. And we obviously need to account for that time in the denominator here to get an accurate prediction of our failure rate. And so we can take that 6 divided by the 17,980, and we can talk about our failure rate as 0.000334 failures per hour. Now, I want you to kind of look at that number and think about what it means, because it's nearly meaningless, right? It's hard to contextualize that result. Like, what does that even mean? Is that a good number? Is that a bad number? How does that relate back to the customer's needs for our products? And that's the specific reason, right? The answer to that question is the reason why we generally talk about reliability in terms of the mean time to failure or the mean time between failure. And so on this slide, all I'm really showing again is that inverse relationship between the failure rate and the theta value, that mean time to failure, the mean time between failure. And we can take this exact same example and we can essentially use this equation to calculate the mean time to failure for our product. So again, we have 20 units, we put them on test, we run them at their normal operating conditions for that full 1,000 hours. Remember, we have 6 units fail, and then here are those time marks, those time values. And we can simply plug in this equation for theta, right? So the mean time to failure, let's say it's a non-repairable unit. So the mean time to failure, we've got the time values. So here are those 6 different time values, plus the 14,000 hours for the 14 units that all passed, divided by 6. And this is a much more meaningful answer. Look at this. Our mean time to failure is 2,996 hours to failure. Now, let's say we're talking about, I don't know, a motor or some other device that we've made. If our customer has told us that, the motor really has to be able to last for 1,000 hours, well, we're good here. The data seems to indicate that our product, meets their reliability needs. If they come back to us and say, no, the product needs to last at least 10,000 hours, well, then maybe we don't have the reliability that the customer needs. So that's the beauty of mean time to failure and mean time between failure, is that those reliability indices really reflect kind of the customer need for our product. The other way we could have calculated this is by simply taking the failure rate from the previous slide, taking the inverse of that failure rate, and we'd come out to the exact same number. Okay, so now we're on to kind of the second part of the presentation, which is all about those reliability models. And so the first model that we absolutely have to talk about is the bathtub curve. It's not a model that we use to actually make reliability predictions. It's a model of the reliability of a unit, of a general device or a general product over time. And the general concept is that when we launch a new piece of equipment, let's say we're talking about either production equipment or even a product, right? When we launch that new product or we first produce a product, sometimes there can be it's an early failure period, right? An early life period where our failure rate is high, but then as time progresses, we work out some of those kinks. Maybe it's manufacturing issues, assembly problems, defective parts or assembly steps that weren't performed correctly. Oftentimes when we first launch a new device or a new automobile, maybe we have this early failure period here that we have to work through. A lot of companies perform like a burn-in, whether it's an automotive company who runs a car for 10 miles or 20 miles or 30 miles just to work out all those early kinks and detect any early failures in the process. But then eventually, most systems achieve this equilibrium period that's called the useful life period. This is where we want to operate. This is where we want our product to be operating in this useful life period. And you'll notice here that the failure rate in the useful life period is constant, right? And by the way, that's lambda. We were talking about that reliability indice of the failure rate. That's what we're modeling here is the failure rate lambda over time. So that's a key characteristic of the bathtub curve, that in the useful life period, the failure rate is constant. And when the failure rate is constant, we can use the exponential distribution to make reliability predictions for our products or for our equipment. So let's look at that now. Let's switch gears now and talk about, okay, we're in the useful life period, our failure rate is constant. How do we make reliability predictions using the exponential distribution? And so let's say we're testing motors, right? And we're making this AC motor. And let's say we have 3 different designs and we've put them all on test and we've calculated 3 different mean time between failure values. The first is 500 hours in green, and you can see how the reliability, right, really kind of tanks really quickly here when we have a poor mean time between failure. The other designs performed much better, right? We've got a mean time between failure of 2,500 hours and a mean time between failure of 5,000 hours. And you can see how this plot of reliability is substantially better over time when that mean time to failure is longer. The y-axis here of this reliability curve is probability, right? It's the probability that your product is successfully performing at that stated instance in time, right? So for example, for this curve here in blue, right here at around 3,500 hours, there's a 50-50 shot of our product failing or performing successfully. And then, by the way, here is the actual equation that we use to calculate reliability using the exponential distribution. And you'll notice there's one parameter here. The reliability distribution is fully characterized by a single parameter, and that's lambda. So we talked about the failure rate. Lambda is really important for the exponential distribution. And then again, remember, that's simply just 1 over theta. So if you're making a reliability prediction and somebody gives you the mean time to failure or the mean time between failure, you can always convert that into lambda. All right, let's do an example real quick. So you've tested 20 units and you found that your mean time between failure is 2,996 hours. What is the reliability of our product at 1,200 hours of operation? So here's a reliability curve of a product that is exponentially distributed, right? We're in that useful life region. And our mean time to failure or mean time between failure is 2,996 hours. Here's how we calculate reliability. So remember, reliability is a function of time. It's e raised to the negative lambda t, where again, remember, lambda is just that failure rate. And now we can simply plug in what we know. So we know we're solving for reliability at 1,200 hours, right? So our t value is 1,200 hours. And then our theta value, you can see theta here in the denominator, is simply 2,996. And when we work out this equation, it comes out to 0.6699. So the question is, how do you interpret that result? Now, if you come over here to the actual reliability graph and you find 1,200 hours here on the x-axis, right, because this is time, you find 1,200 hours and you come across and you go, that looks about right. we have about a 66, 67% reliability at that stated instance in time. Now, you can interpret this two ways. If you think about it as a single unit, the probability that that single unit successfully performs past the 1200 hour mark is 66%, right? Just one unit, the probability of operating past 1200 hours is 66%. If you talk about it as a population, right? Let's say you made 1,000 motors or 1,000,000 motors. At the 1200 hour mark, 66% of your units would still be operational. 66% of your units would still be reliable at 1200 hours, and the other 33, 34% of your units or of your product would have failed by that point in time. Make sense? All right, so now let's move on and talk about the last reliability model that we want to talk about, and this is the Weibull distribution. So this distribution was discovered and popularized by a gentleman named Weibull, and the reason that it's used so often in reliability is because it's able to model a variety of distributions. So I wanted to show you this picture of the bathtub curve again because the beauty of the bathtub curve is it tells us that the failure rate of our product will change over time. Early on in the product's use, we might have this decreasing failure rate in the early failure period. And then over time, we might see our failure rate start to increase here in the wear out period. And the beauty of the Weibull distribution is that it can essentially be used to model any of these parts of the bathtub curve. No matter what the failure rate is of your product, you can use the Weibull distribution to model that data and make reliability predictions using that model. So I've shown you this picture here. You can see how the Weibull distribution can change its shape given some particular parameters. So let's talk about that now. Okay, so here is the equation for calculating reliability using the Weibull distribution, and I've color-coded the two parameters. So the first parameter we have to talk about, this is probably the most important. This is called beta. You can see it here, and it's called the shape parameter, or you might also hear it called the slope parameter, and this parameter dictates the shape of the distribution. So when beta is equal to 3.5, the Weibull distribution approximates the normal distribution. When beta equals 1, the Weibull distribution approximates the exponential distribution. When beta is less than 1, you can see it here at 0.85, the Weibull distribution approximates a system with a decreasing failure rate. And same thing here, when beta is greater than 1, we can now model a system with a increasing failure rate. And this is where the distribution gets its versatility, is from that shape parameter. By the way, I call it beta, a lot of textbooks call it beta, but you need to be really careful. Depending on the textbook you use, you'll see this called by a different parameter. So make sure to pay attention to the way it's described instead of just looking for that Greek symbol beta, because I've seen it called gamma, I've seen it called eta. There's other Greek letters that are used to designate the shape parameter. And then the other parameter that defines the Weibull distribution is theta. Okay, and again, this is that scale parameter. This is that mean time to failure. So for example, when the Weibull distribution takes on that normal distribution shape, that scale parameter essentially stretches the normal distribution out over time, which in the world of reliability is a great thing. It means that our product is performing successfully over time, right? This curve here in blue, all of the products fail at this point in time, right? But when we talk about this curve in gray, it's stretched out over time, right? So we want a larger scale parameter, right? The bigger the scale parameter, the more reliable our product is. And then the other analogy here is back to that mean time to failure. That scale parameter is analogous here to the mean time to failure in that exponential distribution. And you can see how when our mean time to failure is larger, right, our reliability gets kind of stretched out over time. By the way, real quick, before we do an example, I know I said this verbally, but if your beta value is less than 1, your Weibull distribution represents a system with a decreasing failure rate. When beta is equal to 1 here, the Weibull distribution approximates the exponential distribution. When beta is greater than 1, you can see that here. When beta is equal to 2, the Weibull distribution represents an increasing failure rate, a system with an increasing failure rate. And then when beta is equal to 3.5, that Weibull distribution approximates the normal distribution. Okay, let's do an example real quick of a reliability calculation using the Weibull distribution. So let's say your product fits a Weibull distribution and your data indicates that you have a slope parameter of 2. Remember that you can either call it the slope or the shape, right? That's an important parameter. Your data also indicates that your scaled parameter is equal to 8,000 hours. Remember, that's your mean time to failure or your mean time between failure. What is the reliability of your system at the 5,000 hour mark? So this is the point in time at which we're trying to calculate the reliability of our product. So remember, reliability is a function of time. Here's that equation. And so now we can start talking about those parameters. Beta is our shape parameter or the slope parameter, and it's equal to 2. Theta, that's our scale parameter here. And the problem description tells us our scale parameter is equal to 8,000 hours. And T is simply just that point in time that we're attempting to calculate the reliability of our system. So now we can plug in these parameters to calculate the reliability. So it's E raised to the negative, and then we have this fraction, 5,000 divided by 8,000. We square that, and then, of course, we complete the exponent, and we can calculate the reliability at 5,000 hours to be 67% reliable. All right, that was it for today. Hope you really enjoyed it. If you have any questions, shoot me emails at andy@cqeacademy.com. By the way, if you're preparing for something like the CQE exam, I've taken all of these reliability equations and I've put them into a cheat sheet that you can use on the exam to help you be successful. So if you want to get a hold of that cheat sheet, just head over to cqeacademy.com/free cheat sheet. And you can sign up there, get that free cheat sheet, and get a practice quiz to help you prepare for the CQE exam. That way you're as prepared as possible on exam day. All right, if you like this, hit that like button. If you want to stay on this journey to become a CQE, hit that subscribe button and that bell icon. That way as I publish new content, you get notified and you can kind of stay on that journey with me to grow yourself and grow your career. All right, have a great day. Thanks so much. Bye.